Imagine a universe that's a mirror image of our own. This isn't science fiction. This is the realm of antimatter, where particles exist with opposite charges to their counterparts. Instead of negatively charged electrons, we have positively charged positrons. When these antiparticles meet, they annihilate each other in a burst of pure energy. The Big Bang should have created equal amounts of matter and antimatter, yet our universe is overwhelmingly dominated by matter. This asymmetry remains one of the most profound mysteries in cosmology. By studying these elusive antiparticles, we gain insights into the nature of the cosmos. From groundbreaking medical applications to the possibility of interstellar travel, antimatter has captured the imagination of scientists and the public alike.
To study antimatter, we need to create it. This is where particle accelerators come into play. These massive machines, often located deep underground, act as atom smashers. When high-energy particles collide, they generate new particles, including antimatter. The Large Hadron Collider, LHC, at CERN, is one of the most powerful particle accelerators. Protons are smashed together at incredible energies, recreating conditions similar to those after the Big Bang. From these collisions, physicists study the fundamental building blocks of matter. Creating antimatter in particle accelerators showcases human ingenuity and our pursuit of knowledge.
Antimatter is notoriously difficult to handle. Upon contact with ordinary matter, it annihilates in a burst of energy. This makes storage a significant challenge. Scientists have devised ingenious methods to trap antimatter, suspending it in a vacuum to prevent annihilation. One method utilizes electric and magnetic fields to confine antimatter particles. These fields act like invisible walls, preventing the antimatter from touching the container walls. Penning traps, for example, use a combination of electric and magnetic fields to confine charged antiparticles, suspending them in a state of equilibrium. These traps are often supercooled to extremely low temperatures, close to absolute zero, to further minimize the kinetic energy of the antimatter particles and improve their confinement time. The longer we can trap antimatter, the better we can study its properties and explore its potential applications. The development of these trapping techniques is crucial for advancing our understanding of antimatter. It allows us to study its properties in detail, observe its behavior, and explore its potential applications in various fields.
The concept of antimatter didn't just appear overnight. It was first predicted by physicist Paul Dirac in 1928. Dirac, working on a theory to describe the behavior of electrons, stumbled upon a peculiar mathematical consequence. His equation suggested the existence of a particle identical to the electron but with a positive charge, the positron. This prediction was met with skepticism initially. How could there be a mirror image of every known particle? The scientific community didn't have to wait long for confirmation. In 1932, Carl Anderson, while studying cosmic rays, observed a particle with the same mass as an electron, but with a positive charge, the positron. Dirac's prediction had come true. This discovery revolutionized our understanding of the universe. It suggested that for every particle of matter, there exists an antiparticle with opposite charge. This concept of antimatter opened up new avenues of research in particle physics and cosmology. Dirac's work laid the foundation for our current understanding of antimatter. His prediction and its subsequent confirmation demonstrated the power of theoretical physics and its ability to predict phenomena before they are observed experimentally.
Section 5. Annihilation, the ultimate energy release. When matter and antimatter meet, they annihilate each other in a burst of pure energy. This annihilation process is the ultimate conversion of mass into energy, as described by Einstein's famous equation E=mc². The energy released in this process is immense. For comparison, the annihilation of 1 gram of antimatter with 1 gram of matter releases the same amount of energy as the atomic bomb that devastated Hiroshima. This incredible energy density makes antimatter a tantalizing prospect for future energy production and space travel. However, harnessing this energy is a monumental challenge. Producing and storing even minuscule amounts of antimatter is currently prohibitively expensive and technologically demanding. Despite these challenges, the potential benefits of antimatter continue to drive research and exploration in this field. Antimatter annihilation is not just a theoretical concept, it has practical applications as well. For example, it forms the basis of an important medical imaging technique called positron emission tomography, more commonly known as PET scans.
Section 6. Antimatter's medical marvel, PET scans. Positron emission tomography, or PET scans, utilize antimatter in a safe and controlled manner for medical imaging. In PET scans, a small amount of a radioactive tracer, which emits positrons, is introduced into the body. When these positrons encounter electrons in the body, they annihilate, producing gamma rays. These gamma rays are then detected by a scanner, creating detailed images of organs and tissues. This technique is invaluable for diagnosing a wide range of conditions, including cancer, heart disease, and Alzheimer's disease. PET scans provide unique insights into metabolic activity and blood flow, allowing doctors to detect abnormalities and monitor treatment effectiveness. The use of antimatter in PE scans highlights its potential benefits in various fields. It demonstrates how harnessing the unique properties of antimatter can lead to groundbreaking applications with direct implications for human health and well-being. While the amount of antimatter used in PET scans is extremely small and poses no danger to the patient, it underscores the powerful energy release associated with antimatter annihilation.
Section 7. The high cost of antimatter. Antimatter is often touted as the ultimate fuel source, but its production comes at a steep price. Creating antimatter requires enormous amounts of energy, and the quantities produced are typically minuscule. Current estimates suggest that producing a single gram of antimatter would cost hundreds of trillions of dollars. This high cost is a significant barrier to the widespread use of antimatter. The energy required to produce antimatter far exceeds the energy we can currently generate from it, making it an impractical fuel source for the foreseeable future. However, ongoing research and technological advancements may one day make antimatter production more efficient and cost-effective. Furthermore, storing antimatter is another significant challenge. Its volatile nature requires sophisticated trapping mechanisms to prevent accidental annihilation with ordinary matter. Developing safe and efficient storage solutions is crucial for realizing the potential of antimatter as a fuel source or for other applications. Despite these challenges, the potential benefits of antimatter continue to drive research and development in this field. The allure of unlocking the universe's hidden power, however distant it may seem, remains a powerful motivator for scientists and engineers worldwide.
Section 8. Antimatter propulsion, a future among the stars. Antimatter holds the potential to revolutionize space travel. It could achieve speeds approaching the speed of light, enabling interstellar travel. Imagine journeying to distant star systems and exploring new worlds. Antimatter propulsion could make this dream a reality. Even a fraction of light speed would reduce travel times, making Mars missions feasible. While still theoretical, several concepts have been proposed. These designs involve controlled annihilation to produce thrust. Significant engineering challenges remain, but the potential benefits are undeniable. Antimatter propulsion could pave the way for humanity to become an interstellar species. Section 9. Antimatter and the fate of the universe. The study of antimatter has profound implications for our understanding of the universe's fate. The existence of antimatter and its behavior under extreme conditions could hold clues to the ultimate destiny of the cosmos. Some theories suggest that the universe may contain regions dominated by antimatter, forming anti-stars and even anti-galaxies. The interaction between these regions and our matter-dominated universe could have significant consequences for the overall evolution of the cosmos. Furthermore, understanding the asymmetry between matter and antimatter in the early universe is crucial for explaining why our universe is filled with matter and not an equal amount of antimatter. This asymmetry, known as baryogenesis, remains one of the most significant unsolved mysteries in cosmology. The study of antimatter, therefore, is not just about understanding the properties of a peculiar set of particles. It's about unraveling the history, evolution, and ultimate fate of the universe itself. Section 10. Conclusion. The allure of antimatter. Antimatter, once confined to the realm of theoretical physics, has emerged as a tangible reality with the potential to revolutionize our world. From its use in medical imaging to its promise as a future energy source and even as a fuel for interstellar travel, antimatter continues to captivate our imaginations. While significant challenges remain in harnessing the power of antimatter, the relentless pursuit of knowledge and the human spirit of exploration drive us to push the boundaries of science and technology. The study of antimatter is a testament to our insatiable curiosity about the universe and our place within it. As we delve deeper into the mysteries of antimatter, we unlock new secrets about the fundamental nature of our universe and open up possibilities that were once considered science fiction. The journey of understanding antimatter is a journey to the very edge of human knowledge, and it promises to be an exciting and transformative one.